Good morning, everyone. Welcome to Introduction to Electronics and Communication subject. Myself, Darshan B, Assistant Professor, Department of ECE, SJBIT. So today we are going to discuss some topics from Module 1 on Introduction to Electronics and Communication. So these are some Module 1 contents. So in the Module 1, we are going to split into two parts, power supply and amplifiers. Today we are going to discuss on DC power supply. So DC means direct current power supply. See the block diagram of direct current power supply. Here first starting we are considering the high voltage AC. So high voltage AC we consider the Indian standard, the voltage we are going to consider as 230 volts 50 hertz. So that we are going to consider as a high voltage AC as an input. That we are going to apply to step down transformer. So what is the step down transformer? Step down transformer is reduces the voltage level. So we are going to considering the input voltage is 230 volts. We can reduce the voltage up to 15 volts, 12 volts. So that is called low voltage AC. The low voltage AC we are going to apply to rectifiers. As we all know that rectifier converts AC to unregulated DC. So input of that rectifier is low voltage AC. Output of that rectifier is unsmooth DC. Unsmooth DC again that we are going to apply to reservoir or smoothing filter to smooth the wave. Means DC means you should get straight line. Okay, so then smooth DC we are going to apply to voltage regulator. Then we get the regulated DC. So here smoothing circuit or smoothing filter we are going to use the capacitor. So to smooth it. Voltage regulator we are going to use the regulator circuit. Rectifier we are going to use half wave rectifier, full wave rectifier, bridge rectifier. So most of all we are going to use the bridge rectifier to convert AC to DC. So the main input is at relatively high voltage. The step down transformer is appropriate turns ratio is used to convert this to a low voltage. The AC output from the transformer secondary is then rectified using the conventional silicon rectifier diodes to produce unsmooth or pulsating DC output. Then this is then smoothed and filtered before being applied to a circuit which will regulate or stabilize the output voltage so that it remains relatively the constant in spite of variation in both load current and incoming mains voltage. So here the showing the principal components used in that the DC power supply in each block. High voltage AC step down transformer. Here we are going to use the transformer used as a component. Then a rectifier we are going to use the bridge diodes are used in that rectifier. Then the reservoir or smoothing circuit we are going to use the capacitor. Then voltage regulation we are going to use the transistor or Zener diode. The iron core step down transformer feeds a rectifier arrangement. It is based on a bridge circuit. The output of the rectifier is then applied to a high voltage or high value reservoir capacitor This capacitor stores a considerable amount of charge and it is being constantly topped up by the rectifier alignment. The capacitor also helps to smooth out the voltage pulses produced by the rectifier. Finally, stabilizing circuit provides a constant output voltage. You can see that this is the figure 2 indicates that the DC power supply showing principal components used in each block. See that this is the DC power supply, the complete structure. We can observe here. Here we are going to give the AC input, the main supply. So first we are going to use the main filter. This is the primary fuse we are going to use to protect the circuit. This is the main transformer. So transformer converts AC to unregulated DC. This is secondary fuse. Suppose any voltage fluctuations occurs at the main or the secondary of the transformer, so you can protect the remaining part of the circuit. So secondary fuse, reservoir capacitor. The capacitor we are going to use electrolyte capacitor. So ceramic and electrolyte capacitor is there. We are going to use the electrolyte capacitor. Here heat zinc we are going to use for regulator IC 7805, 780, 7812 based on that output voltage. Okay, so we can use 5 volts in a diode, 12 volts in a diode, 7 volts in a diode. Based on the output requirement, we can use and we can convert or we can get the constant output, regulated output voltage. Then we are going to take the DC output voltage from this circuit. Here we are going to apply 230 volts. Here we are going to apply based on our requirement 5 volts, 7 volts, 10 volts, 12 volts. Like that, we can take the DC output voltage at this point. Next, move on to the rectifiers. Rectifiers converts AC to unregulated DC. Here, the semiconductor diodes are commonly used to convert alternating current AC to direct current DC, in which the case they are referred as a rectifier. The simplest form of rectifier circuit make use of a single diode, and since it operates on only either positive or negative off cycle of the supply, it is known as off wave rectifier. You can observe the figure of a rectifier. 230 volt supply or 240 volt supply we are going to apply to transformer. So transformer secondary voltage we are considering as 12 volts. Diode we are going to use. Diode anode is connected to positive, means one end of the transformer. Cathode we are going to connect it to, so through the resistor we are going to connect it to another end of the transformer. Here this is the step down transformer. 240 volts is reduced to 12 volts. The secondary of the T1 or transformer step down to 240 volts RMS to 12 volts RMS voltage, root mean square. The turns ratio of a T1 will be, so 240 is to 12 or 20 is to 1. Based on that, it's going to convert that. So okay, 20 is to 1 ratio. So that 20 times it's going to reduce to 40 divided by 20. So we are going to get the 12 volts. In the positive off cycle of the circuit, diode D1 will only allows the current to flow in the direction shows. So consider from the cathode to anode, that you can observe that current flowing direction there. So D1 will be forward bias during each positive cycle, so relative to common. and will effectively behaves like a closed switch. When the circuit current tries to flow in a opposite direction, the voltage bias across the diode will be reversed, causing the diode to act like an open switch. So you can observe in the figure. So it is a closed switch, this is a open switch. The switching action of the diode results in a pulsating output voltage which is developed across the load resistor RL. So we are going to take the output from this load resistor RL. Since the main supply is at 50 Hz and the pulses of the voltage developed across the RL will be also 50 Hz, even if only half the AC cycle is present. Because we are considering the half wave rectifier, only the positive half cycle diode D1 is forward bias. So in the negative half cycle, so no diode is conducting, the output is 0. During the positive half cycle, diode will drop the 0.6 to 0.7 forward threshold voltage normally associated with the silicon diodes. So the silicon diode cutoff voltage is 0.6 to 0.7 volts. If you are going to use germanium, so it's 0.3 volts. So during the negative half cycle, the peak AC voltage will be dropped across D1 when it is reverse bias. When it's reverse bias means diode acts as a closed or open switch or open, so open circuit, no current will flow. Assuming that the secondary of T1 provides 12 volts RMS, the peak voltage output from the transformer secondary winding will be given as peak voltage is 1.414 into Vrms. That is 1.414 into the secondary voltage is 12. So we are going to get 16.97 volt peak voltage. The peak voltage applied to D1, so approximately 17 volts. Because we are going to consider the VM voltage, maximum voltage. The negative half cycle are blocked by D1 and the only the positive cycle appears across the load. Negative half cycle, so it's open, so that it is considered, so 0 appears across the load. So however, the actual peak voltage across RL will be the 17 volt positive peak being supplied from the secondary on T1. So minus the 0.7 volts, the forward threshold voltage dropped by D1. So this 0.7 volts, why I am telling is 0.7 volt is the diode cutoff voltage or threshold voltage. So in other words, positive half cycle pulses having a peak amplitude of 16.3 volt will appear across the load. Consider one simple the example on half wave rectifier. A main transformer having a turns ratio of 44:1 is connected to 220 volts RMS main supply. If the secondary output is applied to a half wave rectifier, determining the peak voltage that will appear across the load. So consider, we are going to consider that, so 220 volts RMS voltage applied, and they are mentioned the turns ratio is 44:1, so that we are going to get secondary voltage is, so 220 divided by 44, we are going to get 5 volts. The step down transformer output is 5 volt. The peak voltage developed across the rectification after rectification will be given by 1.414 into 5 volts, we are going to get 7.07. So it's passing through the diode, so we have to subtract the diode threshold voltage from this, the peak voltage. The load voltage is 7.07 minus 0.6, we are going to get 6.47. 6.47 volt is appear across the load. This 6.47 volt is the the final voltage at the output. So consider reservoir and smoothing circuit. So it says that reservoir and smoothing circuit, so we can call it as filter circuit. So considering this example for the half-wave rectifier, same as the previous circuit, here we are considering the capacitor. Capacitor is for filtering or smoothing circuit. The capacitor C1 has been added to ensure that the output voltage remains at or near the peak voltage even when the diode is not conducting. C1 is referred as reservoir capacitor. It stores charge during the positive off cycle of the secondary voltage and releases it during the negative off cycle. The circuit of the smoothing or reservoir circuit is able to maintain reasonably constant output voltage across load RL. When the primary voltage is first applied to the transformer T1, first the positive cycle output from the secondary will charge C1 to a peak value across the RL. Hence C1 charges to maximum voltage is 16.3 volt at the peak of the secondary off cycle. Because C1 and R are parallel, the output, the voltage across RL will be the same as the voltage across the capacitor. The time required to C1 to charge to maximum peak level is determined by the charging circuit time constant. In this circuit, the series resistance comprises the secondary winding resistance together with the forward resistance of the diode and the resistance of the winding and connections. Hence C1 charges very rapidly as soon as D1 starts to conduct. The time required for the C1 to discharge is very much greater. The discharge time constant is determined by the capacitor value and the load resistor RL. In practical, load resistor is very larger than the resistance of the secondary circuit. Hence C1 takes appropriately time to discharge, means approximately is more time to take discharge. So during this, the time D1 will be reverse bias and will be held in its non-conducting state. As a consequence, the only discharge path for C1 is through RL. So you can observe the waveform of half-wave rectifier with and without filter. So this is C1 without C1 present. So this is voltage across the RL with C1 present. The secondary voltage waveform together with the voltage developed across the load RL with and without capacitor present. So this is the first waveform is the transformer secondary voltage that we are going to consider. So peak to peak voltage, the minus 17 volts to plus 17 volts. This gives rise to a small variation in the DC component voltage. Since ripple is undesirable, we must take additional precaution to reduce the ripple. So one observed method reducing the amplitude of the ripple is that the simple increasing the discharge time constant. This can be achieved either by increasing the value of capacitor or increasing the resistance value RL. The latter is not really an option because RL is the effective resistance of the circuit being supplied and we don't usually have the ability to change it. Increasing the value C1 is a more practical alternative and very large capacitor value. So consider that 4700 millifarad. So we can use that. you can see them the positive half cycle, it will appear across the load. So you can consider the peak voltage is 17 volts. 17 minus diode cutoff voltage is 0.7, we are going to get 16.3 volts as a voltage across load RL without C1 present. So if you see connected means, so the capacitor is charging and discharging happens. We can observe this. This is the ripple. So AC components presenting in the DC, it is called ripple. So you have to reduce the ripple and you have to get the straight line as a DC output. Suppose if you want to use more filter circuits, the example you can observe in the figure. So this is capacitor C1, so capacitor C2. We are going to use further filter circuit, further refinement of the simple power supply circuit. The circuit employs two additional components R1 and C1, which acts as a filter to remove the ripple. In half-wave rectifier, its efficiency is 40% and ripple is 1.21. You have to remove that ripple so that the voltage of C1 is chosen so that the components exhibit a negligible reactance at the ripple frequency. In effect, R1 C1 act like a potential divider. The amount of ripple is reduced by an approximate factor equal to Xc divided by square root of R square plus Xc square. Xc is capacitor reactance, so R is the resistance.